Hey guys, in this video we're going to be talking about limits at infinity, which should not be confused with infinite limits. In this case, we're finding limits as you approach infinity, and we're not looking for limits that give us infinity. That is the difference between infinite limits and limits at infinity. So let's get started to talk about how these limits work, and let's do some examples on it. So here we have that the function's behavior at large values of x is called the blank blank, right? So large values of x, what do we mean by that? So your behavior at large values means as you go to positive infinity on the right side or negative infinity on the left side. So that is what the large values of x mean, which is going to be called our end behavior of our function. So you may have heard end behavior before in pre-calculus, but an end behavior is actually a limit, and this is how we're going to use it in calculus. So to find the end behavior now, we compute the limit as x approaches 0, infinity, or negative infinity. So I know that it almost seems that we're always computing zeros as x approaches infinity, but the limits at infinity are actually not at all related with 0. They're actually only related with positive infinity and negative infinity, which in this case I didn't say positive infinity, but we assume if I don't say negative infinity that the infinity is positive. Now, for rational functions, the limit as x approaches infinity is the vertical or the horizontal asymptote. So back when I introduced asymptotes, I just told you guys, hey guys, these are the rules, learn these 3 types of asymptotes, and that was it, right? And I actually didn't tell you that the horizontal asymptote is actually a limit. So that is something you learn later now when you learn this part of calculus, that a horizontal asymptote is actually a limit. So here we have the limit as x approaches negative infinity, and negative infinity is going to be the left end behavior, right? The left end behavior. And now as you go to positive infinity, it's going to be the right end behavior. So those are the 2 types of end behaviors that we have and that we're going to compute. So let's go ahead and see this in a graphical example, and then we're going to see how we can translate it to numerical so we can work with any function and not have to be dependent on how the graph looks. So we love this graph 1 over x because it's just used all throughout calculus, and it just comes up all the time, and we just do a bunch of little calculus things on it. And this is just going to be another thing we do on it. We're going to compute limits as x approaches negative infinity and positive infinity on this graph, right? So we already know from rational functions, right, that the asymptotes here are, which we have here, are this vertical asymptote at 0 and this horizontal asymptote at 0, right? But that's what we know. Now let's convert this to the limits, and we're going to compute a graphical limit, which is exactly how we introduce limits. So here we're going to have find the limit as x approaches negative infinity. So here I'm asking you for the left end behavior, right? The behavior of the left side of this graph. So as you approach negative infinity is actually here on the left side, right? So as my graph approaches negative infinity on the x, what is my y value? You guys remember, y values are limits. So what is my y value as I go to negative infinity? So if you guys see, I'm kind of like stopped by this asymptote here. So as I go to negative infinity, I'm going to just stop here. I'm going to border this asymptote, this horizontal asymptote, and that's going to be 0. So graphically, we can see that I'm going to go to 0 as I go to negative infinity. But that's just graphically. In a second, we're going to talk about we can express that numerically. So let's say I ask you now to find positive infinity. So I'm going to tell you, how does my graph behave as I'm going to positive infinity, right? So as I'm going to positive infinity, I'm going to be stopped by this asymptote here of 0. So I'm going to get really close to 0, but I'm just going to say it's 0. As I'm going to positive infinity. The asymptote, it lands on the asymptote of 0. So that is how we see it graphically. But we're not always going to have the graph of every function. So what we want to do is we want to see how numerically we can compute this, right? So as I'm going to go to negative infinity, I'm going to see how my numbers change. So I'm actually going to do the limit as x approaches negative infinity of 1 over x here. I'm going to split this into 2 so I can do the left hand side, whatever. The left hand side and the right hand side. So I'm going to plug in very big negative numbers. So I'm going to see how it changes as my numbers get bigger. So I'm going to start off with 1 over negative 1, 1 over negative 10, and 1 over negative 100. So this right here is negative 1. This right here is negative 0.1. This right here is negative 0.01. And you are safe to assume that as you go more and more negative, more and more a greater number, you're going to go eventually into 0.001, 0.00001. So you guys see how the zeros are not going to stop growing. You're always going to have that 0.0000001. That number is going to be so small because it has so many zeros in front of it. We're just going to call it 0. We're just going to call it 0. Because as you're going to infinity, right? So in this case, you're actually looking at it as you go down because your numbers are getting bigger as you go to infinity. See how here the x value is bigger than it was here. So as you're approaching negative infinity, your x values are getting bigger. So you're actually looking at the number line down now. How are you looking? How are you going as you go down? You're actually getting very, very, very small. Negative, but small. But when you have a number so small as 0, doesn't matter whether it's positive 0 or negative 0. 0 is just 0. So that is what numerically how you would compute it. You would just input really, really, really large numbers, and then you would see that it will go to 0. So now let's do the positive side. So positive infinity of 1 over x, right? What would it be? So let's do it in blue so you guys don't fall asleep and get angry with all this red. And we're going to have 1 over negative 1, positive 1, 1 over 10, 1 over 100, and then maybe 1 over 1,000. Add an extra number in here. But I like doing 3 numbers. I feel like I'm safe with 3 numbers. So here I'm going to have 1.1, 0.01, 0.001, and eventually I'm going to go into 0.001, and so forth, right? So as my numbers are getting bigger, as I'm going to positive infinity, what is happening to my number? It's getting so small, positive, but so small, I'm just going to call it 0. And that is the idea of how you compute a horizontal asymptote or a limit as x goes to infinity or negative infinity. So we kind of already introduced this idea in our previous video when we talked about asymptotes, but now we're going to use it applying calculus, right? And there's going to be some tricks and variations here we got to do to compute this limits. So let's go into some examples on how to do this. So here we have example 1, letter A. So it's going to be very natural for you guys to be like, oh, I remember the rules from asymptotes. If they're the same exponent, I'm just going to make it the coefficients, right? So you really want to just use your previous knowledge of asymptotes and boom, give the answer. But the truth is that there's some work done here. So I think you guys should use the previous knowledge of asymptotes as a checking system. You guys should check your calculus that you guys do with limits. You guys should check your calculus that you do with your previous knowledge of asymptotes. So let's go ahead and do that. So we know that here the exponents are the same, right? That's how we learn asymptotes. When the exponents are the same, you're going to pick the coefficients, and here they're 3 and 1. So here the asymptote is supposed to be y equal to 3. Right? Which, if you guys remember, a horizontal asymptote is a y value, and limits are y values. You see the connection there? So let's erase this. Just give me a second. There we go. Alright, so now how are you actually going to apply calculus and computing this limit as x goes to infinity, right? So what you're going to do is you're going to actually use your rules. And when it comes to computing limits, we're going to be very heavy on factoring. And not factoring as in factoring trinomials, but factoring as in factoring out things. So here we have, yes, we need to write this limit here, always, positive infinity limit, always outside because they might take off points. So let's just write it there and just put it all the way down. Okay, so here we're going to have 3x over x minus 1. So we're going to look at it and we're going to factor things. So what can we factor from the top? You might want to say nothing. But what we're actually going to factor is You're right, nothing. So we're just going to leave the top as 3x. Right? And now we're going to factor out from the bottom. You want to say nothing. But in this case, we're going to factor out x. So we're going to factor out an x. So we're pretty much dividing this by x when we take out an x, right? So x by x gives you 1. And we take out an x from an x, we're dividing it by x, so we get 1. And then we're dividing this 1 by x, so we just get 1 over x. Okay? So that's what we're going to do. We're going to be able to factor out an x. So now let's use the rules of limits that we learned, and we're going to break this up. And what I mean by that is we're going to have, I'm actually going to eliminate this. So we're going to have limit as x approaches infinity of 3x over x. And if you guys see that there's like a multiplication there, I'm going to multiply this and split it into two limits as 1 over that. Okay? So now we're going to go ahead and simplify some stuff. So here I see that I have 3x over x, so I'm going to cancel that out. So the whole thing here is going to give me just 3, and limit as x approaches 3 is just going to be 3. Just 3, right? Because there's no x input, so it's always just going to be a number. Where do you learn that from computing limits? And now we're going to compute this other multiplication. So we're going to multiply 3 times whatever this thing is, right? So here we just have 1. So 1 is just 1. That doesn't matter. Here we just have 1. So there's no x input there. So 1 is just 1. But now we have this 1 over x. What is this 1 over x going to do as you input infinity, right? So the rule is, if the bottom is bigger, right? If you have an x on the bottom and the bottom is bigger, your number is just going to go to 0, right? That's what we learned here. That's what we learned here, that if we have 1 over x, and you input infinity, it's going to go to 0. So whenever you see that that the denominator has a bigger x, right, that the bottom has an x in it, just let it go to 0 when the top is a constant. So this whole thing right here is just going to go to 0. So you're going to be left with 1 over 1 minus 0, which is just, 1 over 1 minus 0, which this whole thing is just 1. So it's 3 times 1. So this whole thing is just 3, which is exactly what you got in the beginning, right? So yes, this factoring thing is a little stupid because we gotta factor all this stuff out, and at the end of the day we kind of know the answer already. But I'm gonna show you guys why you guys need to do this and why it's important, and soon enough you guys will see why. And it just looks nice to do all this calculus, and your professor might actually be annoying and tell you hey, look, you didn't do any work, you have to actually do the limit stuff. And we apply all the rules that we learned about limits, so it's nothing new. We're just applying it in a different way. We're trying to factor out x's. We're trying to factor out the greatest x we can, and then just apply the rules of limits and get our answer. So here we're going to do b, which is going to be kind of the same idea of factoring, but we're going to just factor out something a little different. So we're asked to find n as you approach infinity of n over 2 plus n squared. Okay, so we look at the top. Can we factor anything out from the top? Nope. We just have an n. Let's leave it by itself. Now, can we factor anything out from the bottom? Yep. We have an n squared. So we're going to take out an n squared. Okay? And we're taking out an n squared from the 2. So we're dividing 2 by n squared. So this is going to turn into 2 over n squared. So for the next n squared, if we're dividing n squared by n squared, we just get 1. Okay? So now we're going to go ahead and break this up again into n over n squared. Now we're going to say there's a multiplication sign right there. So we're going to do that. So we just do that, right? So now we're going to simplify n over n squared. We have 2 n's on the bottom, 1 on the top. That's just going to give me a 1 over n. But I still have my limit outside. So I'm going to do that. And then now I'm going to go to the other side, where I'm going to compute my limit on the other side as well. So I have a 1 by itself. That's not going to matter because there's no x there. Or n. In this case, our independent variable is n. We're approaching n as it goes to infinity. So here we have 2 over n squared. So the denominator is bigger, right? Whenever we have an n on the bottom, whenever we have a variable on the bottom, we're just going to let it go to, this whole thing is going to go to 0 because the bottom's going faster, so it's going so big, we're just going to call it 0. So when you're doing limits at infinity, the biggest key is just to recognize that when you have a variable on the bottom, that term is going to go to 0. So this whole thing goes to 0, and then you get 0 plus 1. So you're just getting 1 over 0 plus 1, which this whole thing is just going to be 1, right? Now the question is, how about this guy, right? What does this guy go to? We just simplified it, but we didn't get an answer for it. We didn't get like a 0 or a 1 or something like that, or infinity or something. So here what we're going to say is that when we input infinity, the bottom is bigger, so it's going to go to 0. So now we have 0 times 1, which is just 0, which is our answer to this whole thing, right? So once again, the biggest key here is that whenever we have a variable on the bottom, we just let it go to 0. And if you guys just go back into your rules of horizontal asymptotes, we look where the exponents are bigger, it's bigger in the bottom, and then when the bottom is bigger, the horizontal asymptote is just 0. So yes, you can still use the rules, but I'm about to show you a time that the rules won't exactly help you. So now let's go ahead and compute letter C, which you guys will see has a little twist to it. So let's go ahead and do that. Let me remove myself for a second. There we go. So now we have the limit as square root of x squared plus 1 over x. So we never actually dealt with square roots and variables because we can't really compare the exponents because this exponent is kind of freed. I mean, it's kind of caged by the square root, right? So here our rules will just kind of fail of horizontal asymptote, and you guys will see what needs to get done here. So we're going to do the same thing, which is just factoring, right? That's what I taught you guys to do. Just do a lot of factoring out of the greatest term. So in this case, in this x squared plus 1, the greatest factor is x squared. The biggest x is x squared. And it's going to leave us with, what is, if I take out an x squared from x squared, I'm just going to get 1. And I'm dividing also, the same thing as saying that I'm dividing by x squared, so it's going to be 1 over x squared. And then this right here is just going to be x, so nothing to factor out on the bottom. So now I'm going to go into, I still can't break it up because I don't have 2 terms. So I'm going to keep simplifying in there. So I'm going to actually break it up. I actually have something multiplying inside of the radical. So I'm going to break it up into 2 terms, this term and this term, which is going to give me radical of x squared and radical of 1 plus 1 over radicals. You guys see that? Good. So here we have now radical of x squared. And the most common mistake here is that people just want to say that that is x, right? You think it's x because you've been taught to cancel out an x squared and an x. And at times I'll do it. But when it comes to limits, especially when you're approaching negative infinity, it makes a difference what the answer here is. So we're actually going to drop a little box and show you guys, never to forget this, that the square root of x squared is actually the definition of absolute value of x. So here, it kind of changes our ball game, because if this thing right here would have turned to just x, it would have canceled out with this x here in the bottom. You guys see that? But it didn't. That didn't happen because that right there doesn't turn into x. That turns into absolute value of x. So now we can't cancel this guy and this guy. Okay? Because it's not just x, it's actually absolute value of x. So let's keep on with our problem and see how this would have affected our answer. Negative infinity. So now that we do have a division, 2 factors dividing, let's split it up. So I'm going to have absolute value of x over x times limit of x goes to negative infinity. Okay, so let's deal with this right here, right? So I want to input negative infinity into my absolute value of x and my over x. What am I actually going to get? So what I'm saying here is that absolute value of negative x, absolute value of negative infinity over absolute value of infinity is actually going to turn into the negative absolute value. The absolute value of anything is just positive, so it's going to turn into positive infinity. And when you divide it by this negative infinity, what is that going to give me? So infinity is just a number that we don't know because it's so big, and then we have a negative of that number. Positive infinity divided by negative infinity is just going to give me negative 1. So we're going to say that this whole thing right here just gives me negative 1. Okay? And now let's compute this one here on the right. The 1 is just going to stay as the 1. And then we have 1 over x squared. So we have a variable on the bottom and we're inputting infinity. Doesn't matter that it's negative or positive. We're just going to input infinity into the denominator of a fraction. So that's going to approach 0. So whenever you have an x or a variable in the denominator and you're inputting infinity, that term is going to go to 0. So it's going to be, we already inputted infinity, so we no longer need the limit. So it's going to be the square root of 1 plus 0, which is the square root of 1. Let me remove myself. And the square root of 1 is just 1. So then we have here the negative 1 that we got from the infinities, and then we have here the 1, and we're multiplying those. So the final answer is just 1 times 1, or negative 1. So now that we're done with this problem, you guys can see that it's actually very important to start factoring stuff out and getting in the habit of it, especially when you have radicals. So you might be able to get away with not doing it and being able to check with our old rules of horizontal asymptotes when we don't have radicals. But when we do have radicals, it does become key, and it's very important that we do so. So now we're going to do some practice problems on how this limit as x approaches infinity can be exposed to you. So let's go check it out.